Okay, so once again, we've learned about equations of lines certainly in two-dimensional space, and y equals mxb and y equals mxb can describe a line in two-dimensional space. But what about a line in three-dimensional space? What do we need to describe a line in three-dimensional space? Well, if we go down here, um, to figure 1, okay, you see there a line in three-dimensional space, and the line is parallel to that green vector v in the picture. It's parallel to the green vector v, and it passes through the point P sub 0. Now, P sub 0 is a specific point in space. So if we say that the line must pass through a point and it must go in a certain direction, which is equivalent to saying it's parallel to a vector, then that definitely uniquely determines the line. And the line can be described here if you think about the vector r there. The vector r goes up to a point, another point P on the line. Okay, and if we were to describe a vector equation that would model this line, the vector equation would be given. I want to try to have the vector equation would be given by r, the vector r, equals r sub 0 plus t times the vector v. I mean, if you think about adding, you learned about how to add two vectors. If you look in the figure 1, if you add the vector r sub 0 and then add the vector a, that's going to equal the vector p, right? Tip to tail addition. The vector r sub 0 plus the vector a in figure 1 equals the vector r. But the vector a is parallel to the vector v. So any multiple t of the vector v would be equivalent to the vector a. In other words, well, I want to say that right. In other words, t times some vector v is equal to the vector a. And as p varies, as you trace out the line in space, the point P is going to vary. It's going to have different coordinates, and that means A is going to be different. That'll vary, and then T times V, the T will vary. And so this is a vector equation that describes the line in space, R equals R sub 0 plus T times V. But and that's fine. And then in figure 2 here, you have examples of where that parameter t is negative and when the parameter t is positive, greater than 0. So of course t equals 0 when the point on the line is exactly at r sub 0, because then r equals r sub 0 and t equals 0. But for t greater than 0, the line will move off to the right. You'll be generating points that go to the right, and for t negative, you'll be generating points that go to the left. And so this seems like a very convenient way to describe a three-dimensional line in space. And the general components that describe the line are given by these formulas. So let me just tell you what, let me just go to the whiteboard here for a moment and help make that connection for you. So let me go to the whiteboard, and I'm going to write down for a line here, a line. Here is the vector equation, r equals r sub 0 plus t times a vector v. Okay. Now, the vector r, and maybe what I'll do is do this actually. Let me do this. Hold on. Line again. R equals r sub 0 plus t times v. Okay, the vector r has components x, y, and z. Okay, so this here was the vector equation of a line in space. R equals r sub 0 plus t times v. R sub 0 has components x naught, y naught, z naught. X has components x, y, and z. The vector v has components a, b, c. So this means then that what would x have to equal? If given this vector equation written in component form of a line, what would x have to be? So the left side equals the right side, right? So if that's true, x would have to equal what? Can anybody chat it out? Or tell me?
X naught plus t quantity t times a.
That's right. X naught plus a times t. I think that's, if I heard you right, Hunyu, I think that's what you said.
Yeah.
What would y equal?
Y naught plus b times t.
That's right. Good. And what would z have to equal?
Z naught plus c times t.
That's right. Where have you seen t before? Think about pre-calculus. Hunyu, you have to turn your volume up a little more.
Parametric equations.
Parametric equations, good. And right, Ariane, good. So these are parametric equations. Parametric equations of a line. Parametric equations of a line. Okay. Now, incidentally, while we're at it, based on parametric equations of a line, what does x minus x sub 0 divided by a equal? If we look at the first equation, first parametric equation, x minus x sub 0 over a equals what?
T.
That's equal to t. Good. This whole thing equals t. Okay. What does y minus y 0 over b equal? Based on the second equation.
T as well.
That equals t as well. Good. And then based on the third equation, what is z minus z naught over c equal to?
T.
T. These are called symmetric equations of a line. These are known as symmetric equations of a line. So you have parametric equations of a line, and then you have symmetric equations of a line. Two ways to describe a line in three-dimensional space. Okay. So, are there any questions on this before I get back to the book?
Not yet.
All right. Let's revert back to the book then. Okay, so let's look at an example here. Okay, find equations of a line with a given direction. They want us to find a vector equation and parametric equations for the line that passes through the point 513 and is parallel to the vector I plus 4j minus 2k. Okay, that's part A. So for the solution, well, okay, R sub 0 would equal 513 because the line passes through that point. Now that it's parallel, this line is parallel to the vector I plus 4j minus 2k. So the vector v is I plus 4j minus 2k. And so your vector equation is going to be equal to r plus t times v, which you can write that way, or you can write it as you see below. The vector r, which describes the equation of the line, that vector equation. It's an equation. It's not, it has a variable t in it. T is your parameter. So the vector equation would be the 5 plus t times I plus 1 plus 4t times j plus 3 minus 2t times a vector k. Are there any questions? They have a little picture, by the way, of the situation here, where they draw the line L. Quite beautiful, actually, quite beautiful. You notice that vector v, they don't draw it from the origin. They draw it, you don't have to draw the vector v from the origin, right? You don't have to. Vectors are described by their direction and magnitude. So, but there's a picture. And parametric equations of the line are given here. So once you know your vector equation, you can get your parametric equations. And in part B, where they want you to find other points on the line, you can just let t take on different values, and that'll generate different points on the line. Okay, are there any questions on that? Okay, then let's look at one example here. We'll probably, this example will likely have to do it in 2 parts. But let's go ahead here. Let me give you a moment to copy this down. Okay. All right. Andrew, by the way, I see that you're in the WebAssign, by the way. I mean, I saw that you were able to get in there, like with your account. You successfully got in. Excellent. Excellent. Oh, okay. Oh, Andrew, yeah, I was just mentioning, I saw that I saw that you got in your account now. You have your WebAssign account. So good, good. While you're copying this example, how many of you are gonna, how long does your free access last now? Is it another, maybe, what, 7 days, something like that? What's for WebAssign? Your free trial access, is it another week? Okay, all right. How many are going to wait till they're, okay, 9 days, Ellie says, all right. And how many are going to like wait until the last day to purchase the WebAssign? How many are going to, or, okay, all right, and this, usually a number of students will, I guess, you know, sometimes students hope that, hey, maybe it'll last for a long time. And yes, Gordon, so yeah, if you have a multi-term access account from Calc 1 or 2 at Montgomery College and you took it recently, that ought to work for the access code. All right, very good, Gordon. So, okay, so let's see here. It's 9:30, our brains are tired, but we have to go to 9:40. So but we can handle this. So we want to find parametric equations that, okay, I mean, let's focus on this first part of the problem. We want to find parametric equations for a line that passes through the point 510, but that's but that is perpendicular to this plane. Okay, so a plane, how many remember like equation of a plane, like maybe from pre-calculus, equations of a plane in three-dimensional space had the form ax plus ax plus by plus ax plus by plus cz plus d equals 0. How many recall that kind of thing? Okay, Andrew recalls it. Excellent. And back then in pre-calculus, you were just told, hey, this is the equation of a plane. Have fun, with the planes. Well, in this course, you're going to learn why. You're going to learn why equations of a plane have this form. But for now, take it on faith. Take it on faith. So, okay, now what do we need to determine the equation of a line? We need to know two things. One of them is that point that the line passes through. We got to know a point that the line passes through. But then what else do we need to know about the line? Okay, Gordon, slope. So, and Andrew, slope, but that's right. So slope in the three-dimensional sense means find the blank that the line is going in. Good, Ellie, find the direction that the line is going in. Okay, well, so you're looking here in the problem and you say, well, I don't know what direction the line's going in, but actually you do. You do, because you're told that the line is perpendicular to this plane. Okay, so the direction of the line is determined by the plane. And in fact, you're going to learn that the coefficients of the x, y, and z, so that would be 2, -1, and 1, those coefficients will determine the direction of the line. In other words, because, let me phrase it another way, the plane, the plane has coefficients 2, -1, and 1 in front of the x, y, z. The 2, -1, and 1, those are the components of a normal vector to the plane. So the vector 2, -1, 1, that vector is normal or perpendicular to our plane given as 2x minus y plus z equals 1. So once again, the vector 2, -1, 1, which is found by looking at the coefficients of x, y, and z in the equation of the plane, that vector 2, -1, 1 is perpendicular to the plane. And therefore, since our line is perpendicular to the plane, our line has to be going in this direction, in the direction of the normal vector. Okay? And you'll see this in our next class. But to get to the equations, the parametric equations now, I drew a little picture, and it's just this one page that you're going to be worrying about. Here's a picture of, I just drew a picture of a plane, okay? I'm not trying to draw the plane exactly. I'll let MATLAB do that. But here's an equation of a plane. That's just, you know, the concept. There's a plane. Here's a normal vector to the plane. Okay, I know it's normal because there's the right angle. Okay, and it's perpendicular to the plane. And then here's this line that I'm looking for that passes through 5, 1, 0. Okay. And let me just see here now. One thing. There is a error here. 5, 1, 0 is not on the plane, right? 5, 1, 0 is not a point on the plane. If I substitute 5, 1, 0 in that equation, I'm not going to get, 2 times 5 minus 1 plus 0 is not equal to 1. So 5, 1, 0 is not on the plane. It's off the plane, like maybe say here, 5, 1, 0. So, you know, we won't have that there, right? So there's the line L, perpendicular to the plane and passing through the point 5, 1, 0. And the line L goes in the direction of 2, negative 1, 1. So that means the parametric or the vector form, the vector equation for the line is equal to 5, 1, 0 plus t times 2, negative 1, 1. And based off of that, you can get your parametric equations for the line. Okay. Okay, so here are the parametric equations. And I'm going to ask one question before we sign off here. Two, actually. First, are there any questions? Are there any questions, you know, up to here? Any questions at all?
Yes. What
Yes,
is
Sunyu.
what is the difference with using symmetric equations versus parametric equations?
Well, we'll do symmetric. We could, given these parametric equations, we could write down the symmetric equations. There's really no difference. It's just two ways to represent the equation of a line in three-dimensional space. There's really, but sometimes one is better than the other. Okay, can everybody? Mario's
Okay,
having.
got it. Thank you.
Okay, good. Mario's having audio issue, maybe audio issues. Can everybody hear me? Okay, maybe give me a thumbs up if you can hear me. Okay, good. Mario, this will be in the recording. Okay, don't forget. Okay, thank you, everybody. Now, last question. Could these parametric equations here also be equations for the line L? X equals 5 plus 4t, y equals 1 minus 2t, and z equals 2t. Could those also be parametric equations for the line L? Are parametric equations unique?
They are the same. I mean, they could be the parametric equations for line L because they just differ in multiples of t.
That's exactly right. Very good, Hyunyu. So the 2 here and the negative 1, the 2, sorry, let me get this real quick. The 2, the negative 1, and the 1, those are what you're called the direction numbers of your line. In the second set of parametric equations, 4, negative 2, and 2 are just multiples of 2. So the first parametric equations and the second parametric equations describe the same line. It's just the second parametric equations, the 4, negative 2, and 2, is just 2 times. In other words, what I'm trying to say is 4, negative 2, and 2 is just equal to 2 times 2, negative 1, and 1. Okay, so the direction for both lines is the same. Both lines clearly, the parametric equations, the directions are the same. Okay, and the lines pass through the same point. So both parametric equations both are parametric equations for the line L, so that's a yes. Are there any other questions here before we stop? Okay, who's feeling good? Maybe a few thumbs up if you're comfortable. I always like to end the recording with that. Andrew's good, and Ellie's good. Yu and Kino, thank you. Thank you, everybody. All right, and Ariane and Gordon, excellent. Let me stop the recording. Thank you. Thank you. Let me stop the recording. Let me just get that last person in. I didn't see, hold on here. I always like to get all participants. Oh, Malik, Gordon, and Juliana, excellent. All right, thank you. Let me stop the recording.